Hey everyone, I am Ms. Hu, your physics teacher. In this video, we will be going through an overview of Unit 2, Thermal Physics in the IGCSE Physics 2023 to 2025 syllabus. Now, this video is meant to be used as a revision video or a refresher. So it's targeted to students who have already learned this unit and merely need a quick summary and overview of the entire unit to make sure that they know everything they need to know for their upcoming examinations. So if you are learning this unit for the first time, or if you need revision on specific topics within this unit, please watch my videos on those topics instead. So because this is an overview video, we will be making references to the syllabus guide just to make sure that we've covered everything that we need to know. So let's get started. So first things first, you need to know about the states of matter in terms of solids, liquids, and gases. So knowing about the states of matter is really basic science. It's something that you should have already learned way back in primary. But this basic is also included in IGCSE just to make sure that you have your foundation, and you need to be able to explain the properties of the solids, liquids, and gases based on scientific understanding. So some of you may know, wait a minute, there are more states of matter than these three. For IGCSE, just focus on solids, liquids, and gases. So you need to know their distinguishing properties. Like solid is rigid, it has a fixed shape and volume and cannot be squashed. Liquids are not rigid. They don't have fixed shapes, but they do have fixed volumes, and because of that, they also cannot be squashed. Gases are not rigid. They don't have a fixed shape and they don't have fixed volume, and because of that, can be easily squashed. You do need to be able to relate their properties to the particle arrangement as well as the forces between the particles, but we will cover that in the next slide. For now, let's just go through number 2, which is that you need to know the terms for the changes in state between solids, liquids, and gases. So from solids to liquids, the process is known as melting, while from liquid to solid, it's freezing. From liquids to gases, there are two processes, evaporation and boiling. So this particular image only mentioned one. I've added another one here in another font. And from gas to liquid, the process is known as condensation. Now, between solids and gases, you don't need to know the names of the processes. Of course, for general knowledge, it's good to know. But for IGCSE exams, you don't need to know about sublimation and deposition. Now, you also need to know about a particle model for solids, liquids, and gases. So you need to be able to describe the particle structure of these three states of matters in terms of the arrangement, separation, and motion of the particles, and represent these states using simple particle diagrams. You also need to know about the forces and distances between the particles, whether atoms, molecules, ions, and electrons, and how the motion of these particles affect the properties of solids, liquids, and gases. So generally, you need to know, of course, that in solids, they have very strong intermolecular forces between the particles. Liquids are moderately strong, while gases forces are negligible. In terms of particle arrangement, solid particles are very close together in a regular pattern. Liquids are close together, but the arrangement is random, while gases are very far apart and very random in terms of their arrangement. For the movement of particles, solid particles vibrate around a fixed point in space. Liquids move around and over each other, while gases move quickly in straight lines in random directions until they collide, causing them to change direction. So this motion is explained in Brownian motion, which we will cover shortly. As mentioned, for the shapes and volumes, solids have fixed shape and volume, while liquids' shapes are not fixed. They take the shape of a container, while the volume is fixed. Gases don't have a fixed shape or volume. They take the shape of the container and expand to fill the container in terms of the volume. While for compressibility, solids are not compressible, liquids not really compressible. In fact, the compressibility is very small, almost negligible, while gases are highly compressible. When drawing out the particle models for solids, liquids, and gases, make sure that when you draw the solid particles, they are all stacked neatly in a regular arrangement. Liquid particles have random arrangement and there's a little bit of a distance between them, although they're very near each other. Whereas for gases, you need to draw the particles far away from one another in random arrangement. Now, in terms of the motion of microscopic particles, what you need to know is that the random motion of microscopic particles in a suspension is evidence for the kinetic particle model of matter. You do need to be able to describe and explain this motion, which is sometimes known as Brownian motion, in terms of random collisions between the microscopic particles in a suspension and the particles of the gas or a liquid. And you need to know that the microscopic particles may be moved by collisions with light, fast-moving molecules, and correctly use the terms atoms and molecules as distinct from the microscopic particles. So what are all these actually explaining? Basically, you need to know Brownian motion. When observing the microscopic particles, for example, pollen seeds in water or smoke particles in air, when observing them under the microscope, you would observe those dark color particles moving in a random fashion. So you've got this zigzaggy motion. So how the particles move is also important to note. They're not in curved lines. So you'll find that they move in straight lines and then change direction randomly. So straight line, change direction, straight line, change direction, straight line, change direction. So the changes in directions are random. They're not following any particular order, and all the motions are in straight lines. This can be explained through the collision of the invisible particles. So for example, the pollen seeds in water, the reason for the changes in direction is because they collide with the invisible water particles. So here collides with a water particle, changes direction, collision with another water particle, change direction, and so on. Same thing with the smoke particles. So the smoke particles could be colliding with the invisible air particles. So travels straight, collides with air particle, travels, collides another air particle, and so on. So the motion of the particles are always in a straight line. The reason for the changes is because of the collision with the invisible particles that seem to cause them to randomly change direction. So that's what you need to know about Brownian motion. For thermal expansion, you need to be able to describe qualitatively the thermal expansion of solids, liquids, and gases at constant pressure. So you must remember that gases, because the particles are the furthest away from each other, when heat is applied, gases will have the greatest expansion, followed by liquids, and solids have the least in terms of the thermal expansion. You also need to describe some of the everyday applications and consequences of thermal expansion. So an example of a consequence of thermal expansion for solids, we know that on a hot day, roads can expand. So when it comes to bridges, they need to make sure that there is a gap in between so that if the roads were to expand, there's space for the expansion and the bridge won't buckle and possibly crack. Another example would be how cables are placed on the pylons. They're not placed tight. There's a little bit of a sag because the cables on a hot day could also expand, while on a cold day they could shrink. So if the cables were to shrink, what happens is the pylons could be pulled towards one another and topple over. So that's why the cables always have a little bit of sag to, number one, allow the thermal expansion and the thermal shrinkage to take place. So that's why there's always a sag when they hang the cables, so that there is space for the cables to be able to expand as well as shrink depending on the temperature of the weather. An example of an application would be to enable us to open a tight bottle. So we find that the cap is too tight. What we can do is we apply heat on the cap so that the cap expands, and then we can open the cap on the bottle more easily. Now you also need to be able to explain in terms of the motion and arrangement of particles, the relative order of magnitudes of the expansion of solids, liquids, and gases as their temperatures rise. So as mentioned earlier, gases have the greatest expansion because they have the greatest distance between the particles. Liquids a little bit less because the distance between the particles is less. While solids, because they're right next to each other, there's very little distance between the solid particles. The expansion is much lesser compared to liquids and gases. So just to show you why you need to know about the states of matter, it has come up before in a past year question, as recent as in one of the summer papers in 2023. So in this question, they ask students to identify which state of matter has the greatest thermal expansion and which has the least. And they also require students to describe in terms of motion and arrangement of particles the structures of solids and gases. And this is the marking scheme at the bottom. So just to let you know, based on many of the past year questions that we've seen, most of the comparisons are always between solids and gases because they're the most contrasting in terms of their properties. It's very easy for students to be able to show the differences clearly and also makes it easier for the examiner to mark. That's not to say that liquids won't be tested, it's just that usually it's easier to give an answer and to mark when the two comparisons needed are completely contrasting. So do be aware of how to draw and state the differences between solids and gases, but don't neglect liquids, just in case it comes out. Next, gas pressure. So you need to be able to describe the pressure and the changes in pressure of a gas in terms of the motion of its particles and their collisions with a surface. And you need to describe the pressure and the changes in pressure of a gas in terms of the forces exerted by particles colliding with surfaces, creating a force per unit area. So what's all that? Okay, in general, what you need to know are two different things. First of all, you need to be able to describe how gas particles are able to exert a pressure. So when you are asked to explain how gas particles exert a pressure, make sure you talk about the collision of the gas particles with the walls of the container. A common mistake that a lot of students make is that they talk about the collision between gas particles with each other. Now, gas particles do collide with each other, but pressure is exerted on the container. So that's why you need to talk about the collision of the gas particles with the walls of the container. Don't bother mentioning the collisions between the gas particles themselves. Talk about the collision between the gas particles with the walls of the container. So the collision produces a change of momentum, which is impulse, as you learned in Unit 1. And this impulse causes a force, also known as impulsive force. This force per unit area is what produces the gas pressure. So as you can see, you need to relate the collision of the gas particles with what you have learned in Unit 1. The change of momentum causes a force, and this force per unit area will get us gas pressure. So how you remember this is that it's actually a logical step-by-step process. So first of all, talk about the collision, which leads to a change of momentum, force, and then pressure. Now, the second thing you need to know is to describe how the changes to the gas pressure can cause changes to other properties. For example, a change in the volume or the change in the temperature. So, when you want to talk about the changes to the gas pressure, you do need to talk about how there's more collisions, and more collisions produces greater change of momentum, which leads to more pressure. You do need to know how to tweak this a little bit depending on what the question is asking. For example, if the question asks how the increase in temperature changes the gas pressure, then you need to talk about how that increase in temperature with more kinetic energy leads to that change in gas pressure. So I'm not going to go into that in detail right now, I'm just pointing this out in general that you need to be aware of. And when answering the questions, be clear about these two different kinds of questions, because a common mistake that I see students make is that the question asks about gas pressure, but students talk about changes to gas pressure. To give you an idea of what I'm talking about, let's look at some past year questions. This is a recent paper on winter 2022, paper 4. So in this question, students are asked to explain in terms of the momentum of particles how a gas exerts a pressure. So this question does not ask how the gas changes pressure, it asks how a gas exerts pressure. So as you can see, this is a general question, it's not a relationship question. So to provide the answer, you must mention the term momentum and how this momentum exerts a pressure. And you can refer to the mark scheme here. The mark scheme includes what I have just suggested that you include. You must mention the particles have momentum or the particles hit walls. Collision, right? There's a change in momentum when the particles hit the walls. There's a force exerted due to the change of momentum, and pressure is a total force per unit area. For question B, the temperature of a sample of gas is increased at constant volume. State and explain any change in the pressure of the gas. So question B is asking the students for the relationship between the temperature and the pressure. So to answer this question, first of all, students must mention what the change is, which is that the pressure increases, and the explanation is to explain how the temperature changes the pressure. So you can mention that there is a greater change of momentum, or that the particles exert a greater force, or that particles move faster, or that particles have more kinetic energy. So here's another example of a question taken from Winter 2023 paper. The temperature of the bottle and its contents are increased. Explain in terms of particles how the air pressure inside the bottle changes as the temperature increases. So this one is also a relationship question where they ask students the relationship between temperature and pressure. So similar to the previous question, you can mention any of this, but this time it's a 3-mark question, so you do need to make sure you mention at least 3 of any of this following. And then for question 2, it's just asking how the air pressure changes when the lid is removed. So the pressure decreases because some of the air particles escape from the bottle. Now let's go to absolute temperature. So you do need to be able to describe the relationship between the motion of the particles and temperature, including the idea that there is a lowest possible temperature known as absolute zero, where the particles have the least kinetic energy. So you must also know absolute zero, which is actually 0 Kelvin. This is 0 Kelvin, not okay. 0 Kelvin. The value of 0 Kelvin, or absolute zero, is equal to negative 273 degrees Celsius. And that's because from the graph, if we were to plot a graph of the temperature of a gas against its pressure in degrees Celsius, you actually get a linear graph. And if you were to extend this graph, we'll get a value of negative 273. So absolute temperature, which is in the Kelvin scale, is obtained by taking this graph and shifting it forward 273. That's why to calculate the temperature in Kelvin, you just take the temperature in degrees Celsius plus 273. So the number 273, very important when it comes to absolute temperature. You also need to be able to describe qualitatively, in terms of particles, the effect on the pressure of a fixed mass of gas when there is a change of temperature at constant volume as well as a change of volume at constant temperature. So for this, you just need to know the general relationship. So for example, in this diagram, let's say these 2 bottles are the same bottle, but in the first situation, the temperature is cooler, and in the second situation, the temperature is hotter. That means we apply heat. So in the first bottle, the particles are of course moving less because cooler temperature, there's less kinetic energy. Whereas when it's heated up, there is more kinetic energy, so there's more movement in the bottle, and that's why there's more collisions leading to greater pressure. So you have to know that when the temperature increases, I'm going to write in symbols here, when the temperature increases, the pressure increases if the volume was constant. In the second diagram here, let's look at a container where the volume can change, for example, a balloon. So if we have the same balloon, but we are able to change the volume at a constant temperature, we need to see how the pressure changes. And how you can visualize it is this. Because the temperatures are constant, that means the particles will be moving with the same kinetic energy. But if the balloon now has a greater volume, the particles are moving with the same speed and same kinetic energy. They have further to travel in that larger volume. Hence, the pressure will be much lower. So I'm going to write it in short form here, that when the volume increases, the pressure decreases. Now, in addition to knowing the general relationship, you also need to be able to calculate this out. But you only need to know this for pressure and volume. Temperature and pressure, no need. So the only formula you need to know in this case is PV equals constant. This is actually Boyle's law, but you don't need to know the name for IGCSE. So for a fixed mass of gas at constant temperature, you need to know how to solve questions involving the changes numerically. So P is pressure and V is volume. So say this is the first situation and second situation of the exact same balloon with the same mass of gas inside. This first balloon will have a certain value of pressure and volume, and the second balloon also has its own pressure and volume. You need to be aware that because PV equals a constant, therefore P1 V1 equals to P2 V2. Now we do know that the increase in volume causes a decrease in pressure, or even the other way, an increase in pressure could cause the volume to decrease. They actually have an inverse relationship. So graphically, the relationship between pressure and volume, doesn't matter whether P is on the X or Y axis and vice versa. An inverse relationship would have a curved graph like this. So this would be the graph that represents the relationship between pressure and volume of a gas. So that's pressure being inversely proportional to volume. Another kind of graph that you may need to know would be this. Because pressure is inversely proportional to volume, or as you can see, pressure is directly proportional to 1 over V. If you plot a graph of P against 1 over V, you'd get a directly proportional relationship like so. So just be careful when you're looking at graphs. You need to see what's on the Y and X axis. So if it's just P and V, then the relationship is inversely proportional. You get a curved graph like this. But if it's P against 1 over V, then it's a directly proportional relationship, straight line. Let's move on to specific heat capacity. So what you need to know is that a rise in temperature of an object increases its internal energy. Duh, right? An internal energy, there's actually two types. You have the kinetic energy and the potential energy, which is between the particles. You also need to be able to describe an increase in the temperature of an object in terms of an increase in the average kinetic energy of all the particles in the object. So remember that temperature represents the average kinetic energy of the particles. You also need to be able to define and calculate specific heat capacity. So specific heat capacity is the energy required per unit mass per unit temperature increase. And how you remember the definition? Just refer to the formula. So C is the specific heat capacity, while E is the energy applied to increase the temperature, M is the mass of the object, and theta is the change in temperature caused by the heat applied. This is also quite commonly written as E equals mc theta. So it's not a problem if you wrote the formula that way and you use it in the exam as E equals mc theta. You also need to be able to describe experiments to measure the specific heat capacity of a solid and liquid. So the experiment for specific heat capacity of a solid usually involves the aluminium cylinder. So you have the aluminium cylinder here. So we have the aluminium cylinder, which comes with two holes. The larger hole is where we place the electrical heater. And the smaller hole is where we place the thermometer. So in the experiment to determine the specific heat capacitor is based on the formula where the electrical heater provides electrical energy. So we calculate the electrical energy using the formula E equals PT, where P is the power of the electrical heater and T is the total time the heater was providing heat to the cylinder. M is the mass of the aluminium cylinder, and theta is the change in temperature that is recorded by the thermometer. So if we wanted to measure the specific heat capacity of a liquid, we could use water that we place inside this kind of apparatus, which is known as a calorimeter. There is a container inside where we'll put water. This is the heater, which will be heating up the water, and there is a hole here where you can put the thermometer. So similar to the experiment for the aluminium, we would calculate the energy provided by the heater using the formula E equals PT. The mass, of course, is the mass of the water, and theta would be measured from the thermometer that we place in the water, and we get a change in temperature between the initial and final temperature. So that's the experiments for the specific capacity of a solid and liquid. You also need to know about melting and boiling. So you have to be able to describe melting and boiling in terms of energy input without a change in temperature. So yes, when materials undergo melting or boiling, which are changes in states, they will absorb heat, but there's no change in temperature, as shown here in this heating graph. So when looking at the graph, you also need to be able to identify the states of matter at different points on the graph. For example, in this experiment, if we started from a solid state and we start applying heat, so the increase in temperature here would be the solid, change in state here would see a constant temperature, so there's both solids and liquids during the melting phase. Once it's completely liquid, then the temperature goes up again, and then when it reaches the boiling point, the liquid would boil. So during this constant temperature phase, it contains both liquids and gases. If somehow we were able to trap all the gas particles in a container and continue to apply heat while measuring its temperature, you'll find the gas particles will also continue to increase in temperature. You also need to know the melting and boiling temperatures for water at standard atmospheric pressure, which is something you should have already known since you were a kid. The melting temperature for water is of course 0 degrees Celsius, while the boiling point is 100 degrees Celsius. You also need to know about the process of evaporation. You need to be able to describe evaporation in terms of the escape of more energetic particles from the surface of a liquid. You need to be able to describe how temperature, surface area, and air movement over a surface affect evaporation, and explain the cooling of an object in contact with an evaporating liquid. So let me just address number 4, 5, and 8 first, which is where you need to be able to describe the process of evaporation and what happens. So when explaining how evaporation occurs, you must make sure you use the term escape of more energetic particles from the surface. So these are the key words you must use, because evaporation only happens at the surface. The inner particles here can't evaporate. Why do the surface particles evaporate? Because they have the most energy. Why do they have the most energy? Because they absorb energy from the other particles, whether other particles in the liquid or even the surrounding particles. So once the particles have enough energy, they're able to break the bonds between the particles and then escape out into the air. So the reason why there is a cooling of the liquid as well as cooling of any object in contact with the evaporating liquid is because those energetic particles have absorbed energy from them. Like I mentioned just now, the energetic particles have absorbed energy from the other liquid particles or from the surrounding. For example, could be the beaker. So because the liquid and the beaker have lost energy, that's why they have a cooling effect. So some examples where you might need to be able to explain this would be, why is it that sweating produces a cooling effect? So the reason is because the water particles have absorbed heat from the skin. Once the particles gain enough energy, they will be able to leave the surface of the water. So that leaves behind a cooling effect because the skin has lost energy to those water particles. Now, in terms of the factors that affect evaporation, you need to know how temperature, surface area, and air movement over a surface affect evaporation. Now, this is very logical, so by right, you shouldn't be memorizing this so much, yeah? It makes sense, right? So when the temperature increases, so I'm going to write short form here. Obviously, when the temperature increases, there's more kinetic energy. Therefore, the rate of evaporation also increases. So I'm just going to write E here as evaporation. Now, if the surface area increases, that means there's more surface for the water to be able to escape. Obviously, the evaporation rate will also increase. And if there's air movement, like wind, like blowing, or if you switch on the fan, obviously that also allows the evaporation rate to increase because that air movement helps give energy to the water particles to be able to evaporate. Now, you also need to be able to describe the differences between boiling and evaporation. The few differences you need to know: evaporation can take place at all temperatures, but boiling only takes place at a boiling point. Evaporation is a slow and gradual process, while boiling is rapid and violent. Evaporation only takes place at the surface of the liquid, while boiling takes place over the entire liquid. Evaporation causes a cooling effect, while boiling does not produce cooling. Now let's go on to the thermal energy transfers. So there are three you need to know, which are conduction, convection, and radiation. And we will start first with conduction. So these experiments involve rods where thumbtacks or pins are attached to them with wax. So the materials of the rods could change depending on the experiments. For example, different metals or different materials like metal versus glass. And we observe how the thumbtacks fall off the rods, or which one the thumbtacks fall off the fastest. Importantly, you need to be able to describe thermal conduction in all solids in terms of atomic or molecular lattice vibrations, and also in terms of the movement of free or delocalized electrons in metallic conductors. So remember that thermal conduction is the transfer of heat energy from a hotter region to a colder region, because hotter particles have more energy and the energy is being spread out to the area where there's less energy. How thermal conduction typically happens? It is a transfer of thermal energy through collisions. So for example, if we were to look at this diagram, say we heat up one end of this rod. As this particle gains heat energy, it starts to move faster and faster, and it transfers some of the energy to the next particle through collision. Then as this particle gains energy, it then transfers the heat to the next particle also through collision. And that's how thermal conduction occurs. Now, this happens in all materials, whether solids, liquids, or gases, just that we find that it happens the most quickly in solids because solid particles are right next to each other. Liquids and gases, possible but very difficult, because in liquids and gases, convection tends to take over, which we'll cover in the next slide. Now, this also happens actually in all materials, whether non-metal or metal, but in metals, there's an additional method of thermal conduction. In this case, the movement of free electrons. As you should know by now, metals have a lot of free or delocalized electrons, which are free to move on the surface of the metals. So if heat was to be applied to the metal, not only do the atoms absorb heat, the electrons also absorb heat. And because the electrons are able to move a lot more freely, as electrons gain heat, they will move easily throughout the entire metal very quickly. So the electrons will help to transfer heat energy, because as electrons move, they will collide with other electrons or even other atoms and transfer the heat energy to those particles that they collide with. So that's why metals are such good thermal conductors. Non-metals do not have these free or delocalized electrons, which is why in comparison, non-metals don't conduct heat as easily. So remember that when you talk about thermal conduction, for non-metals, talk about the transfer of thermal energy from particle to particle through collision. Whereas for metals, you need to focus on the movement of free or delocalized electrons and how these electrons transfer heat also through collisions with other particles. Next, you need to know about convection. Now you need to know that convection only takes place in fluids. That means liquids and gases. You also need to be able to explain convection in liquids and gases in terms of density changes and describe experiments to illustrate convection. So we have on the side here a diagram just to show us what happens during convection. So let's say we have the heat source at the bottom. Obviously, the particles at the bottom are the ones that's going to get hot first. Now, as the particles get hot, they decrease in density because, as you should know by now, hotter objects have lower density because for the same mass, the volume is now bigger. Thermal expansion, right? So the volume is larger, so density decreases. Lower density materials will always rise, so the hot fluid will rise up. The colder fluid, because they have higher densities, will sink. So the cold fluid sinks and then become really close to the heat source. So the cold particles will now gain heat from the heat source, and as they get hotter, then they will rise up, and the particles that have risen up would have lost a little bit of their heat, making them cooler, and then they will sink in comparison to the other particles. So what happens is there will be a convection current due to the exchange in places between the hotter and cooler particles. So this keeps taking place, and of course eventually the entire container of fluid would kind of be about the same temperature, but the convection current will still happen because the particles at the bottom will always be hotter due to the proximity to the heat source. So that's what happens in convection. Thermal radiation does not need any medium because it's quite simply infrared radiation, and all objects emit this radiation. The hotter an object is, the greater its infrared radiation, which means the greater its thermal radiation. Thermal energy transfer by thermal radiation does not require a medium, which means that they can travel through a vacuum, which is how the thermal radiation from the sun is able to reach Earth, because the thermal energy needs to travel through space, right? And space is a vacuum. And yet we can still receive the heat. So yes, thermal radiation does not need a medium, can travel through vacuum. You also need to be able to describe the effect of a surface color, whether black or white, and a texture, whether dull or shiny, on the emission, absorption, and reflection of infrared radiation. So emission and absorption are not the same thing, but we do find that the colors and textures that are good emitters tend to be good absorbers as well. Because if they're good at absorbing, they're also good at emitting. And they also are usually poor reflectors. Whereas good reflectors tend to be poor emitters and absorbers. So what you have to remember is that the color black and the dull textures are very good emitters and absorbers, but very poor reflectors. Whereas the good reflector and poor emitter and absorbers are silver and white colors, and they have shiny textures. Now, although in the syllabus it only says black or white, I've included silver in here because actually the best reflector is silver, which is why mirrors have a silver surface, or shiny metals are excellent mirrors. Although not required to know, it is good knowledge to have. So in addition, also you need to be aware that for an object to be at constant temperature, it needs to transfer energy away from the object at the same rate it receives energy. So because as we know by now, all objects emit thermal radiation. So yes, for example, a cup of water may be emitting thermal radiation, but it's able to remain at a constant temperature if it were receiving the same amount of thermal radiation from other sources. Now, what will happen to the object if the rate at which it receives energy is less or more than the rate at which it transfers energy away from the object? So it makes sense, right? If, let's say, it was receiving less energy than how much energy it's being released, obviously it will lose its thermal energy, so the temperature drops. So if the rate of receiving energy is less than the rate of transferring, obviously the temperature will drop. Whereas if the rate of receiving energy was greater than its rate of transferring, then the temperature would obviously increase because it's receiving more thermal energy. Logical. You also need to know how the temperature of the Earth is affected by factors controlling the balance between the incoming radiation and radiation emitted from the Earth's surface. So where is Earth receiving radiation? From the sun. So as the sun emits radiation, it will be received by the Earth. So some of it would be absorbed by the Earth's surface, some will be absorbed by the clouds and the atmosphere. Some of the radiation may be reflected back. So whether the Earth gets hot or cold depends on how much energy is being received and how much energy is being emitted out. So obviously in the daytime it's a lot hotter because the sun is emitting a lot of radiation, and the emission of heat by Earth is a lot less than how much radiation is received by the sun. So some of the heat may be reflected away, some of the heat may be absorbed by the atmosphere or the clouds, but the fact remains that there is still incoming solar radiation. However, at night, there's no thermal radiation being received by the sun. So any of the thermal radiation that was being absorbed by the Earth is now constantly being emitted without any absorption. So that's why at night, the Earth is losing temperature, so it gets a lot cooler. In addition, you also need to be able to describe experiments to distinguish between good and bad emitters of infrared radiation, good and bad absorbers of infrared radiation, and you need to know how the rate of emission of radiation depends on the surface temperature and surface area of an object. So an example of a radiation experiment could be something like these, where we have the heat source in the middle, and then we have the objects placed at equal distances from the heater. So they could have different colors and different surfaces. For example, you could have one in matte black or dull black. You have shiny silver or polished silver, or white or shiny white. You can even mix it up. You could have it as dull white or shiny black, just to have a comparison. So in the first diagram, we have containers of water, where the containers have different colors and textures. And we use water as the medium with which we will measure the change in temperature. In the second diagram, if we don't use water, you can just have a sheet with that color and surface. And although it's not in the diagram, you should actually have a thermometer to measure the change in temperature. So by measuring the change in temperatures, we can then determine whether those colors or textures are good or bad emitters or absorbers of infrared radiation. In terms of the rate of emission of radiation and how they depend on the surface temperature and surface area of an object, this is also quite logical, because obviously if the surface temperature is higher, then the rate of emission would also be higher, because greater temperature, more energy to release. I'm writing this all in short form. If the surface area was greater, also the emission rate would be higher, because there's just more surface from which the radiation can be emitted. So in this case, you just need to be able to describe. You don't really have to explain. And you need to be able to identify what kind of thermal transfer takes place, whether conduction, convection, or radiation. So you need to explain some of the basic everyday applications and consequences of conduction, convection, and radiation, including heating objects such as kitchen pans and heating a room by convection. So for example, you need to explain how a kitchen pan is able to get hot through conduction, where the heat source heats up the atoms, which then transfer energy through conduction. Or if it's a metal pan, then of course the free or delocalized electrons would then help with the thermal conduction. And also you need to be able to describe how a room can be heated by convection. So for example, if we were to use a heater, where would you place it? At the top or the bottom of a room? Now obviously at the bottom, because when you place the heat source at the bottom, this heats up the air particles and hot air rises. So the cold air would then fall and get heated up by the heater, and then that hot air will rise again. If you were to place the heater at the top, the air stays hot at the top, the air at the bottom stays cold, so you will never be able to heat the room successfully. You also need to explain some of the complex applications and consequences of conduction, convection, and radiation, where more than one type of thermal energy transfer is significant, including fire burning wood or coal, or a radiator in a car. So that means in this case, the question they give you could be a situation where there's more than one type of thermal transfer, and you need to identify what's happening and which is which. So for example here, this is neither fire or a car, but this diagram also shows us all three. So if we have a kettle boiling water, this kettle gets conduction because the kettle absorbs heat from the fire, and the metal atoms of the kettle will be transferring heat throughout the metal through conduction. The water in the kettle would experience convection currents because water is a fluid, so the hot water particles at the bottom closest to the fire would then get hot, they'll rise up, and the cold water would then sink to the bottom, get hot by the fire, and then the whole convection current just moves that way. There's also radiation because fire is a heat source and it releases heat through thermal radiation. So that's it for Unit 2 in a nutshell. So if you found this video to be educational and helpful, please click like and subscribe for more physics lessons from your physics teacher, Ms. Ho. It will also be great if you could help me keep making free educational video lessons and lab practicals. I do accept donations at my Ko-fi page, which is ko-fi.com/physicsrocks. And if you would like to get notes, quizzes, and syllabus updates, do visit my website at physicsrocks.com. Happy studying and all the best for your upcoming examinations.